Welcome back to Miles Maths. This is the second video on the product rule for counting. However, we're going to call this product rule for counting extended. This is aimed at GCSE students at a high level, perhaps top set year 10, top set year 11, or students extending their knowledge prior to going on to doing A-level, or students perhaps looking at entering the maths challenges, the UKMT maths challenges and so on. To begin with, what we're going to do is just recap a couple of things from the first video on product rule for counting. So we're just going to do a couple of quick examples. So if we looked at EG1 and we said that perhaps there were 20 football teams in a league, and we looked at how many matches the teams were going to have to play all together, well, we'd say, well, if I was a particular team, I'd have to play 19 other teams at home. However, there would be 20 teams all saying that, so all 20 teams would be playing 19 games at home against teams which would be away. Hence, I'd have 20 times 19, which would be 380 games altogether in the league. I might also consider a second example. I might consider Nick, and Nick perhaps has a kitchen with 3 doors, so we'll call this Nick's kitchen. Nick's kitchen has 3 doors. It has one there, it has one down here, and it has perhaps one over here. And Nick works out, he wants to know the number of routes he can take through his kitchen, and he thinks, well, if I start at A, if I label them A, B and C, if I started at A, I could go out through door B, and if I started at A, I could also go out through door C. However, if I came in through door B, I could go out through door A, or I could go out through door C, and of course, if I came in through door C, I could go out through B, or I could go out through A. And this is clearly 6 routes through Nick's kitchen. However, there's another way of thinking about this, and that is that I could say, well, there's 3 ways in, and once I'm into the room, if I'm not going to exit by the same door, there are two ways out. And so 3 times 2 is 6, and hence there's 6 routes through Nick's kitchen. And these are both examples of the product rule for counting. Product rule because we are using the product and we're multiplying 2 things together. We then went on in the first video to talk about choosing 2 girls to go and see the mayor, and we said we were going to choose 2 girls, and it turns out there were only 5 girls in the school. So, so how many ways were there of choosing 2 girls from 5 girls? Well, I think we just said, well, when I go and choose the first girl, I've got a choice of 5. When I go and choose the second girl, I've already chosen 1, so there's only 4 girls left. However, Anna with Mary is Anna with Bella is the same as Bella with Anna, so it doesn't matter which way round they are. So I can halve that, and I can say 5 times 4 is 20, halved is 10. So there are 10 different ways of choosing these 2 girls to go and see the mayor. Today's video is really about what happens if I extend this problem and we start to look at choosing 3 girls. Now, I don't want to start with choosing 3 girls from 5. I'd like to start with choosing 3 girls from a school of 3. Well, clearly I've got some possibilities. I can think about this. I can write these down. I can have Anna, Bella, and Claire, or I can have Anna, Claire, and Bella. But they're actually the same thing. They're just duplicates. I could have Bella, Anna, and Claire, or Bella, Claire, and Anna. But they're all just still duplicates. Or I could have Claire with Bella and Anna, or I could have Claire with Anna, Bella. And these are clearly all just duplicates of the first one. I mean, there's only one way to choose it. I've got three girls, and I have to choose 3 girls. I have to choose all 3. There is only one way of doing this. Mathematically, though, I can write this down the way we've been writing this down before. I can say, well, my number of ways is 3, because first time I choose, I've got 3 girls to choose from. Then I choose my second girl, there are only 2 to choose from, and then I choose my last girl. However, when I look at the duplicates, I now haven't got 2 duplicates that I'm dividing by. I have 6, and the reason I have 6 is because there are 3 girls that I have to choose from, and then 2 girls I have to choose from, and then 1 girl. And so I end up with 3 times 2 times 1 over 3 times 2 times 1, which is, of course, 6 divided by 6, which is, of course, 1 possibility. And there it is. It's Anna, Bella, and Carol. So what happens then if I extend this problem and say, well, let's choose 3 girls to meet the mayor, but now let there be 4 girls in the school. Well, I can use this same diagram, except I can continue the argument. And I can say, well, instead of A, B and C, I can have A, B and D. Donna is now involved. However, I realise there are duplicates of this. And there will be duplicates in the same, sort of mirroring this one. So I really only have to list the first one to think about how many I've got to deal with. So having got A, B, D, clearly I could have perhaps A, C, D, or of course I could have no A at all, just have B, C, D. And clearly for each of these, I've also got my duplicates. So, how am I going to work out the number of ways I can do this? Well, the number of ways must be, first choice, I had 4 different girls I could choose from. Then I had 3 different girls I could choose from because I'd already chosen 1. I've now chosen 2. So I have 2 girls left I can choose from. However, for each choice, I have 6 duplicates. Therefore, I have to divide by 6. Where does the 6 come from? Well, it comes from the 3 times 2 times 1, as it did up here. Now, this is easy enough mathematically. We can go and get an answer to this. However, it's interesting to note that if I just add a times 1 on this top line, I end up with something quite interesting. 4 times 3 times 2 times 1 is 4 factorial. And 3 times 2 times 1 is 3 factorial. And there's a button on a calculator to do this, which means I can start to work this out very quickly. Clearly the answer is 4. You can go and check that on a calculator if you wish to. However, we can do this by just cancelling fraction here and taking out the 1s, taking out the 2s, and then cancelling off the 3s. And we can see that our answer in there would just be 4. And there it is. So what if we end up with a bigger situation where we choose 3 girls from 5? What do we get apart from 2 very disappointed girls? Well, if we go back to the top up here, clearly we can have Anna, Bella and Claire. However, we've got to think about the 2 girls that are left over. So let's choose 3 from 5, number of ways. So we would start with 5 girls this time. And we'd pick 1 from 5. We'd then be left with 4, and we'd pick 1 from 4. We'd then be left with 3, and we'd pick one from 3. We know how many duplicates we have. We have 3 times 2 times 1 duplicates. But as with this problem, this doesn't lend itself to doing on a calculator very easily or very nicely. However, we can make it work on a calculator really nicely just by saying, well, what if I just made this into 5 factorial? What would I have to do to the bottom line in order to make this work? Well, clearly I'd have to multiply by 2 by 1. And I just have to multiply these two numbers together. Now clearly, this just cancels out as a fraction. However, what I've turned this rather neatly into is 5 factorial over 3 factorial, 2 factorial. So, what I'm really doing here is I'm saying I'm going to choose any 3 from 5, and these are the not chosen. So at this point, I could consider writing this down as some sort of formula. We actually give all of these things letters. We call any choose, we call these R. We call this N. And because this is clearly the not chosen, this is N minus R. In this case, it's 5 minus 2, giving me, 5 minus 3, 5 minus 3, giving me the 2, N minus R. So, we denote this in various ways mathematically, which you won't see at GCSE, but you will see at A level. We can show this as NR in brackets, or we can show it as NCR, like this. And we can basically say this, whilst we say it as NCR, we can regard this as N choose R. So, for example, if we were saying 5 choose 3 is how we would write this. So NCR would be N factorial over R factorial N minus R factorial. And this is known as the binomial. So 5C3 is of course 5 factorial over 3 factorial. 5 minus 3 gives me 2 factorial. Now I can just do this on a calculator. So I could do this by saying 5, and then my factorial button is just in there on this particular calculator. It's a little exclamation mark. And I could divide that by 3 factorial times 2 factorial, close my brackets, which equals, and I can end up with 10. So there are 10 ways in which I can choose 3 girls from 5. I could have worked this out, looking back at this particular calculation here, by just cancelling down. I could have cancelled down the 2 times 1s off the end. I could have cancelled out clearly then cancelled out the 3s. I could have divided the 4 by 2. And got a 2 there, and ended up with 5 times 2 is 10. So, using this little formula for finding the number of ways, we can then go on to do a sort of an extended example. So, that should have been EG6. Let's go and label up EG7. For EG7, we're going to use some counters. We're going to use some little little bit of practical kind of manipulatives here. And here we have 6 counters. These are from an Othello set. They are white on one side and they are black on the other. So by giving them a quick shake and kind of dealing them out, I can see that I got 1 black and 5 whites in this case. However, wouldn't it be nice to know the number of ways there are of getting 2 black counters? Well, clearly here's one way. I could have 2 black and then 4 white. However, I could perhaps have black, white, black, white, white, white. Or I could have black, white, white, black, white, white. Or I could have blacks at both ends and whites in the middle. How many different ways would there be of doing this? Well, my number of ways of getting 2 blacks well, I can use my little formula. I can say this must be 6 factorial. I'm picking any 2 to be black, divided by 2 factorial. And the ones that aren't black would be 4 factorial. I can run this through my calculator. Alternatively, I can write it out longhand. I can write this out as 6 times 5 times 4 times 3 times 2 times 1. And 2 factorial is 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And clearly I could do a bit of cancelling in here. Just cancel the 1s, cancel the 2s, cancel the 3s, cancel the 4s. And I would end up with 6 times 5, which is 30, divided by 2 times 1, which is 2. 30 divided by 2 is just 15. So it turns out there are 15 different ways of doing this, and I can do that in pretty well in seconds. So now, how many ways then, number of ways of having 1 black counter? Stop the tape now and go and work out, using the little formula, how many ways there are of just having 1 black counter. Okay, you should be back. The number of ways that we have of doing 1 black counter would be 6 factorial over 1 factorial, 5 factorial. You should come up with the answer 6. This is very sensible. Here are my counters. This is one way. Here's a second way of having 1 black. Here's a third way, a 4th way, a 5th way, and of course the 6th way of having 1 black. So now can you work out the number of ways of having 0 black? Stop the tape now. Okay, you should be back. Well, clearly this is 6 factorial over 0 factorial, 6 factorial. Now, if you do this on a calculator, you'll find that this actually comes out as 1. And the reason for that is because 0 factorial is actually defined as being 1. So what I've actually written here is 6 factorial, which is 720, over 1 times 720. Whoops, missed the 2 out. Which is clearly 1. And if you think about it, that's completely logical. How many ways are there of having no black counters? That one, no others. Now I can now extend this into slightly, and this is getting now away from GCSE slightly, but certainly a sort of problem that comes up in the intermediate and the senior maths challenge, which is looking at this with regards to probability. And the question looms of well, how many possible different outcomes are there? Well, this of course would be, you could work this out. You could work out how many there would be with no black, how many there would be with 1 black, how many there would be with 2 black, how many there would be with 3 black, and you could add them all together, you know, when you got to the end. But it's a very long-winded way of doing the problem. The truth is that when you pick that first counter, so if you only have one counter, then there is literally two possible ways it can be. It can be black or it can be white. So its ways is just two. However, when you have two counters, you have this counter, and then you could say, well, for whatever this counter is, you can either have this one black or you can have this one white. So let's see what that looks like. We can have two whites, we can have two blacks, we can have white black, or we can have black white. That's 4. However, if I had 3 counters, whatever I had here, I could either have a white with it or I could have a black with it. So I'm doubling the number of possible options. So this would have to be 8 ways. And then logically, it doesn't matter what these came before it. When I introduce a 4th counter, I double the number of possible options there could be. It could either be black or it could be white. Hence, I'm doubling the 8 I already had. So for 4 counters, I would have 16 different ways that I could arrange them. Now, you should be able to recognise this, that this is 2 to the 1, this is 2 squared, this is 2 cubed, and this is 2 to the power 4. Hence, if I have n counters, I should be realising that there are 2 to the n ways of arranging them. This allows me to look at this and say, well, 6 counters, there must be 2 to the 6 ways of arranging them. 2 to the 6, 64 ways of arranging them. Hence, if I now want the probability that I just take these counters and I give them a shake, drop them down, and I get 2 black. So the probability of 2 black, well, there are 15 ways of getting 2 black out of 64 possible outcomes. And I can extend this to probability. We're now going to do a brief some brief questions on how, on an 8th example, and you can go and work the answers out. I'll allow you to stop the video each time. I'll allow you a second or two to do that so that you can go and work out the answers, and then I'll give you the answers. So this is going to be EG8. This is going to be our final example here. We're going to introduce 2 additional counters onto this. So we're going to say, can you find the number of ways of getting 3 black from 8 counters? Please stop the video now. Okay, hopefully you're back with an answer. What we're actually looking for here is 8C3. So we're choosing 3 from 8. So this is 8 factorial over 3 factorial, 5 factorial. And if we run that through a calculator, 8 factorial divided by 3 factorial divided by 5 factorial gives us 56. Excellent. Next question. Can you give me the total number of ways 8 counters could land? I'll turn off I think you should turn off the video now and just have a go. What are the total number of ways that these 8 counters could land? Okay, hopefully you're back. Of course, the way to do that, we learnt down here. And we can say the total number of ways this could land would just be 2 to the power 8. 2 to the power 8 is 256. So, finally, what is the probability that we shake the counters up and we get of the probability of 3 black counters from 8? Stop the video now. Clearly this should just be 15. 15. What am I talking about? Absolute rubbish. 56 divided by 256. And that's product rule for counting. Linking into binomial and probability.